right. Every once in a while I forget that. Okay, so so here's the beginning of the recording. I already kind of started sharing my screen and talked a little bit about the problems that we're going to be covering in this lab, but we're going to I'm going to be going into some detail about how to do this and working an example. What I want to do now is upload a couple of documents to you that will eventually get on Canvas. I need to get them onto Canvas, but for right now, for today, they're available for you in the chat to download. Okay, and again, if you're watching the recording later, hopefully by then I'll have them up on Canvas. I have to work on that this weekend, getting that set up. All right. So what are these two documents? Well, the first one that I uploaded, this is a writable version for me, are a series of these kinds of problems. And you can see, so you can see that you're in these problems, you're given a formula, you're given an NMR spectrum, you're given an IR spectrum. I made these quite a while ago, and I put the NMRs first. It doesn't really matter what order you put them in, but I tend to myself use NMR a lot more than IR. We'll talk about that, but these are some of these examples. I'm going to be working the first example for you in just a moment. The other thing that I uploaded is this file. This is an NMR correlation table. When I made the PDF really quickly yesterday, I guess I opened up a Word document. I guess it reformatted or whatever, so it looks a little funny. So I'll see if I can fix it before I put it up, but at least you have it. So this is similar to the IR correlation table, which you can also use in reference to this, where these numbers are the chemical shift numbers. In other words, the numbers where the peaks appear relative to the scale on the bottom. And then what these are represent then is the types of hydrogens, the types of structures that give peaks in these ranges. Okay, and you can see there's quite a lot of them. So today I'm going to be sort of also kind of narrowing down that list just to the ones that are going to be most relevant right now, because the first set of NMR problems that we work are going to be relatively simple, the structures. They're not going to represent all of the possible complexity that we could introduce in these problems. Okay. All right. So these are the notes from my lecture yesterday, and I'm going to go ahead and just cover these again so that we have them in our thing. They do kind of basically explain what we're doing here. And then I have, as I said, an example problem to work with you guys, which will kind of give you an idea of how this works. So these kind of problems, I'm just going to warn you, they can be frustrating at the especially at the beginning. They're puzzles, basically, with a particular sort of format and everything. Some people like working puzzles, and for some people, working NMR problems ends up being something they really like. But some people don't like working puzzles, and in that case, you're probably not going to like these very much. So but we'll keep working with you, and you'll have to just keep asking questions and whatever. And although it looks, I think it in the beginning, it looks really complicated and it's really abstract. In the end, you'll see that it actually is fairly understandable once you invest a little time. Okay, so what I'm going to talk to you about today then is solving NMR IR structural problems. So the fundamental NMR IR problem is this: given a formula, an IR spectrum, and an NMR spectrum, determine the structure of the molecule. So your answer is basically going to be a Lewis structure of a molecule. So what I'd like to do is first walk you through some basic steps that I recommend to help you solve this. Like, what, you've given all of this information, where do you start? So this is my recommendation. It's not perfect. As we advance in this, and we're going to do this again, we're going to add on to our NMR stuff and everything next semester. And as we do this, they'll become more complex, and there'll be other things that we have to consider. But for right now, these steps really should get you pretty far towards solving these problems. Okay. So the first thing we're going to do is we're going to look at the formula that's given. As I said, in all of the problems that we're going to work this semester, you will be given the molecular formula of the molecule. That's really valuable because the formula represents the set of atoms that you have available to be able to build the structure of this unknown molecule. And so we're going to look at it, and almost all formulas are going to have carbons and hydrogens because that's what organic molecules have. But then there are other atoms that often appear in organic molecules. And we call many of these, the electronegative ones, we call them heteroatoms. And here's a brief list of some example heteroatoms. So oxygen and nitrogen and chlorine and bromine, and there's other ones. These are probably, this short list here is probably the majority of the ones that you will encounter in the structures this semester. Okay. And it's important to look at the formula and identify which heteroatoms are present, because one of the things that we see when we look at the NMR correlation table, I'm just going to show you over here, down here. So if you look, let's look at this. So when there's a hydrogen on a carbon, and then that carbon is also attached to a chlorine, that hydrogen will absorb at a chemical shift between 4.1 and 3.1. When there's a hydrogen attached to a carbon, and that carbon's attached to an oxygen of, say, an alcohol, that hydrogen will absorb at a chemical shift between 3.8 and 3.2. And while it may not be completely obvious, this range of numbers and that range of numbers overlap. And so the problem is that if you look at an NMR spectrum and you say, oh, look, here's a peak at 3.5. And you go to the correlation table, well, you might look here and say, oh, okay, that must mean that I have a hydrogen attached to a carbon attached to a chlorine. But that will only be correct if there's a chlorine in the formula. If there's no chlorine in the formula, then even though the correlation table says hydrogens attached to carbons with chlorines are in this range, and I have a peak in that range, it must be caused by something different. And so that's where it's really important to keep the formula in mind. What you're actually going to see for the majority of these is that most of these formulas are going to have oxygens in them. Oxygen is by far the most common heteroatom in organic molecules. Okay. And that's actually not a bad thing, because we can use, oxygens, when they are in organic molecules, have three basic structures, okay, as with that, that involve only carbons and hydrogens, okay? So oxygens and carbons and hydrogens form only three basic substructures in a molecule, okay? Now, there are other structures. For example, oxygens can form structures with nitrogen or with sulfur and whatever. But again, if you don't have a nitrogen or you don't have a sulfur, you won't see those structures, okay? So here are the three basic structures, okay? The first structure is oxygens can form a hydroxyl group, an OH group, connected to a carbon. And we see that structure in certain functional groups. We see it in alcohols, and we see it in carboxylic acids, and we see it in phenols, which are, I wrote this really awkward, they're phenyl alcohols. Oxygen can form a double bond structure with carbon. So carbon, double bond, oxygen, and we call that a carbonyl. And we see this in a variety of organic functional groups. We see it in aldehydes, we see it in ketones, esters, carboxylic acids, amides, and there's even a few others that we probably will not see in structural problems this semester, but we are going to learn a couple others of these next semester, okay? Finally then, oxygens can form a structure where there's a carbon on one side, there's an oxygen in the middle, and there's a carbon on the other. And we see this in functional groups like ethers. We also see this in esters, okay? And so when we have an oxygen, we basically expect to see one or more of these structures, depending how many oxygens there are, in the molecule. Well, what's really useful about this for us, if we're trying to determine the structure of a molecule, is that two of these structures, OHs and C double bond Os, are directly visible as peaks in an IR spectrum. So let me review that with you. Now, you can get the IR correlation table, and you can look at these numbers and verify what I'm saying. But basically, when we discussed IR earlier this semester, we looked at the correlation table and we looked at the kind of structures, and we saw that, for example, we could have an OH structure in an alcohol, and that would give a very specific type of peak in the IR. And that peak is either a fairly sharp peak at 3,600 wave numbers, the IR units, and that occurs when the oxygen is not able to hydrogen bond, which is relatively rare. Or more commonly, we would get a broad peak from around 3,400 to around 3,200. It would look something like this. And we saw several IRs that had that feature. OHs are also part of carboxylic acids, when an OH comes from a carboxylic acid, the absorption in the IR looks a little bit different. It's still a broad, strong peak, but it's way broader. It goes from 3,400 all the way down to 2,400. And so you don't really get a sense here in these drawings, but the alcohol peak would be right there, whereas the carboxylic acid peak is way bigger. The other thing about the carboxylic acid peak is that very often there's these spikes up here around 3,000, which represent the fact that in that region, the OH bond is absorbing IR, but then also CH bonds are absorbing IR and they add up. Okay. C double bond O's are also really clear to see in the IR. What we see if we look on the correlation table is that for basic C double bond O's of esters, carboxylic acids, ketones, and aldehydes, we get peaks. We get a peak between 1,800 and 1,700. And I drew it down here. It usually has a shape somewhat like this. We'll be seeing one of these shortly in a real IR spectral problem, okay? And the only complication with C double bond O's is that very often C double bond O's are conjugated with carbon-carbon double bonds, which means that we have a carbon-carbon double bond, then a single bond in between, and then the carbon-oxygen double bond. We call that conjugation. And what conjugation does is it causes the frequency of that to shift to a lower frequency. So for example, something that might absorb at 1710 if it weren't conjugated would now absorb maybe at 1690 or 1680, okay? And so we just have to kind of be careful. And then finally, amides, which is another carbonyl functional group, these already have an effect that lowers the frequency of the C double bond O. And so they generally come, in the neighborhood of 1650, sometimes a little higher, very often maybe a little lower, but they'll still be a carbonyl peak, okay? So those are some of the things that we can look for in the IR, okay? And then finally, with regard to this, there's one other thing to think about, which is if you have an oxygen and you look in the alcohol region and there's no peak, and then you look in the carboxylic acid region and there's no peak, and then you look in the carbonyl region and there's no peak, well, then that means that you have this ether-like structure, because that's what's left, right? And so we can both determine structure by looking at what we do have, the peaks that are present in the IR, but then as we get better, we can also look for the peaks that should be there if we have some of these structures and are not present, right? That gives us also information. Okay. Once we've looked at the NMR, the IR, we're going to go over to the NMR. We're going to get a lot more information from the NMR. So the first thing we want to do when we look at the NMR is we want to look at the integration, okay, and the number of signals. So what I'd like to do is I'd like to start working on our example and sort of show you how this works. So here's our example, and actually we're going to go ahead and do the first part with the IR spectrum just to sort of show you how all that stuff that I talked about really works, okay? So when we look at our formula, you can see that we have 2 oxygens in our formula in addition to the carbons and the hydrogens. So now we're going to look at the IR. Here's the IR spectrum. Now, as we said, we could have an OH, but to have an OH, what we would need to have in our IR spectrum is a broad peak shaped sort of like that. This would be an alcohol OH, and you can see that we don't have that. A carboxylic acid OH, this is not a totally accurate picture, but it would be a broad peak like that. And you can see we don't have that. So do you see that's valuable information about the structure? The other thing we could have is a carbonyl. And we actually do have that. Do you see this is a very strong C double bond O peak, okay? And we don't have the exact number given. That's sort of a shortcoming of these particular things. But, you know, looking at it, it's maybe at 1730 or something like that. And we could look on the IR correlation table and maybe get a clue about what functional group that is. Now, that's one of the oxygens. Notice that we have two oxygens. We don't have two C double bond O peaks, which you would have if you had two C double bond O's. So most likely the other oxygen is sort of an ether-like thing. So that's going to be something to keep in mind. All right. So when we're working this problem then, what we can say for certain right now is that we have a C double bond O structure in our molecule. So what I do when I'm doing this, and actually I should do this in a different color, but what I do when I'm doing this is I draw the structures as I sort of work them out. And then I subtract the atoms that I needed to build that structure from my formula. Because once I know I have this structure, those atoms become unavailable to make other structures. So now I just have to figure out what the rest of the atoms are doing. Okay. Excuse me just a moment. Hey, come here. What's wrong? Sorry, my cat came in and was like meowing at me really loudly. All righty. So that's that. So basically, that's all the information we're going to get from the IR. You can see we don't get a huge amount of information, but we get information potentially about things that we don't directly see in the NMR, because in the NMR, the hydrogen NMR, we really only directly see the hydrogens. And so a C double bond O, for example, has no hydrogens. I'm going to show you that we can see in the NMR clues that we have a C double bond O based on the chemical shifts. I'll show you that in just a moment. Okay, so going back then to our analysis of our NMR, the first thing we're going to look for is our integrations. Okay, and integration, that's a concept that was covered in the NMR problem lab earlier this semester. So you may want to go and review that and that lecture. Okay, but the basic idea is that a hydrogen absorbs some of the radio energy that's being sent into the NMR, and that absorbance causes a peak. And when you have multiple hydrogens that are equivalent, and again, that was covered in the lecture, but equivalent hydrogens are, in a sense, hydrogens that are kind of the same because of symmetry or whatever, they behave the same, or you could rotate them and put each hydrogen in the same place and then you would get the same molecule. So when you have equivalent hydrogens, each of those hydrogens will absorb some portion of the radio energy we put in. And so the total amount of energy absorbed will add up. And that will appear in the NMR spectrum as an increase in the area of the peak. Now, these NMR spectrum were made on a very strong instrument, an instrument with a very large magnet. And the stronger the instrument, the narrower the peaks become. And it can be a little hard to see how there's areas under here. But these really powerful instruments have computers to analyze and present the data to us. And the computers can work out the area. And in this particular one, the computer not only worked out the area, but what it did was it did a calculation where it sort of determined the ratio of the areas. And it presented that information as these numbers right here. So these are the integration numbers, and they represent the ratio of areas of the peaks. But what they also then represent is the ratio of the number of hydrogens giving that signal. And so, for example, it's saying 3 hydrogens gave this signal, 3 hydrogens gave this signal, 2 hydrogens gave that signal. And if we look at the number of hydrogens we have only 8 hydrogens, and 3 plus 3 plus 2 is 8. So all of the hydrogens are accounted for in these signals. Okay, so why is the integration useful? Well, there's a couple things about it. So, for example, if we look at a methyl group, which is a really common structure in organic molecules, occurs at the end of chains, it can occur as branches, things like that. 3 hydrogens attached to the same carbon. The methyl group hydrogens are all equivalent. And so they're going to absorb in the NMR at the same frequency. And they're going to give a signal that has an integration that's a multiple of 3. So the way you get an integration of 3 hydrogen in most cases is to have a methyl group. Similarly, if you have 2 equivalent hydrogens, that usually represents a CH2. Now, there's some exceptions to that. Sometimes CH2 don't give two equivalent hydrogens. We will see that next semester, but for the most part, the NMRs that we'll be doing this semester, if you have 2 hydrogens, that probably means you have a CH2. Okay, so let's go back and look at our example NMR spectrum. And in our example NMR spectrum, you can see we have 3 hydrogens here. So that probably represents a CH3. We have 3 hydrogens there. So that probably represents a CH3. And we have 2 hydrogens here. That probably represents a CH2. Now those CH2s and CH3s are attached to other things, and we're going to use additional information in the NMR spectrum to tell us what they're attached to. But just knowing this, if you'll notice, this adds up to 3 carbons, 8 hydrogens. That's all of the rest of the carbon and hydrogen in the molecule. So we have a lot of information about this structure already. The next thing we're going to look at is the splitting. Now, again, the splitting was covered in that lecture. And you may or may not remember in that lecture that when I taught you guys about splitting, I used my analogy of people in houses, where the houses were essentially the carbons and the people were the hydrogens. And we talked about how when we have several houses next to each other, that you can have a really interesting situation where, for example, you can have a house, that house can have 1 person living in it, but then there's a house next door with 2 people. So this house with only one person has two neighbors. So we have the number of people in the house itself and then the number of neighbors. So the number of the people in the house I mentioned was basically what the integration tells us, right? It tells us how many hydrogens there are on a given carbon. But the splitting tells us the number of neighbors. And what that begins to give us clues about is which houses are next to each other, which carbons are connected together, right? Right now, if we look at our sample, our example NMR, we know that we have methyl groups and CH2 groups, but we don't know which of these are connected together, right? So the splitting is going to tell us that once we learn how to interpret it. Okay. Well, how does that work? Well, there's a basic rule. It's called the N+1 rule, and it says the signal for a hydrogen that has N number of neighbors will be split into N+1 peaks. So if you have N+1 peaks, that means that that hydrogen has N number of neighbors. Now, there's some patterns that we see. Probably two of the most common are this, where you have 3 peaks. They actually have this sort of relative height for reasons that we will talk about next semester. But basically, we call this sort of shape in the NMR, we call it a triplet. It's 3 peaks. And because it's 3 peaks, right, N+1 equals 3, that means we have 2 neighbors, right? If N+1 is 3, then N is equal to 2. We also see this kind of structure. This is called a quartet. Again, it's sort of this relative shape usually. It's 4 peaks. And so if N+1 equals 4, then N equals 3. So that's 3 neighbors. Okay, so now imagine a situation where we had this structure. We had a CH2 attached to a CH3, and then no neighbors on the other side of the CH2. Okay, so these 2 hydrogens on the CH2 would be equivalent. So I mark them hydrogens A, and then these 3 hydrogens on the methyl, the CH3, would be equivalent. So I mark them hydrogens B. Okay, and if we looked at the integration, hydrogens A would have an integration of 2. And hydrogens B would have an integration of 3. If we then look at hydrogens A and we say, how many neighbors do they have? Well, here's the carbon next door, and it has 3 hydrogens. So N is equal to 3. Similarly, if we look at hydrogens B and ask how many neighbors do they have? Well, here's the carbon next door. It has 2 hydrogens, so they have 2 neighbors. If you have 3 neighbors, then the signal here would have an integration of 2, and it would be split into 4 peaks. Integration of this methyl would be 3, and it would be split into 3 peaks. Overall, if we look at this, this is an ethyl structure. It's an ethyl group. So an ethyl group has a really common pattern in the NMR. There will be a CH2 with 4 peaks, and then there will be a CH3 with 3 peaks. Let's go look at our NMR spectrum. So if you look, you will see that here we have a CH2. Do you see there are 4 peaks? So N+1 equals 4, N equals 3, 3 neighbors. Over here, do you see the 3 peaks of the triplet? So what this is telling us then is that the carbon that has these hydrogens on it is connected to the carbon that has those hydrogens on it. Now notice that this signal and that signal are not directly next to each other in the peaks in the NMR spectrum, okay? The order of these peaks is not really directly related to the way they're connected in the molecule. It's related more to the electron density of the hydrogens. And so we'll see that this is consistent with that electron density, but what we can see is the splitting will tell us which carbons, which peaks are on carbons that are connected to each other. So the upshot of the whole thing is that this and that are part of an ethyl group. So what we're going to do is we're going to draw an ethyl group up here. Okay. We're going to subtract the atoms that we needed to make that ethyl group. And now all we have to work out is what's going on with this CH3. We actually already know we have a CH3. So we'll go ahead and put that up here too. And we have an oxygen, and we don't know where the oxygen is connected yet. So we're just going to put that. It doesn't really matter where we draw these right there. And in fact, now we have nothing left. So these are the pieces that we have in our molecule. Now we just have to figure out how they're connected together. Now you'll notice in these structures, I have these bonds with these dots on the end. Those dots are going to be what we're going to connect together to make the overall molecule structure, okay? And I'm going to show you now how we can work out which dots are connected to which. Okay, so I wrote the heading and then I ran out of room. So to work out what dots are connected to which, what substructures are connected to each other, we're going to use the chemical shift. The chemical shift relates the position of the peaks, the numbers down here where the peaks come, to sort of substructures and different things that we see in organic molecules, okay? The correlation table I've given you, as I pointed out, it has lots of different things. What I'm going to do is summarize a few of the most common ones that we will probably see in our simple NMR problems that we're going to be working at for our first assignment here. Okay, so let me just go through these. So the first one is, I'm going to start on the left and work to the right, just so that they're kind of in an order so that it's not just jumping all over the place. So the first range that we see peaks in, is 8.0 to 6.5. In that range, these peaks represent hydrogens that are on aromatic rings, okay, phenyl hydrogens. Now, if you imagine that you have a phenyl group in your molecule, a benzene ring has 6 hydrogens, but to attach a benzene ring to a larger molecule, we're going to have to take one of the hydrogens off and then use a bond on that carbon to attach to the molecule. You see, here's our dot. And so just a simple phenyl group with only one thing attached to it will be 5 hydrogens. And so we often see 5 hydrogens in this region. if we have two things attached, and I put them right next to each other, but that's really, we could have them attached next to each other. We could have it attached here, which is meta. We have them attached there with this ortho. We're going to talk more about that next semester. You can see that to attach two things to the ring, you have to take two hydrogens off, so you'd have only 4 hydrogens. And again, it's not unusual to see 4 hydrogens in the integration in that region. Now, there's a couple things I want you to know about this. This absorption can be broken up into multiple signals because technically, for example, not all of these hydrogens are equivalent. And so non-equivalent hydrogens can absorb at different frequencies. They also behave as neighbors to each other, so they can have splitting. And the total number of hydrogens can be 5 or 4 or 3, depending on how many substituents are on the ring. If I go to our sample spectrum, we don't see it in this one, but on the next one, see this next one, compound 2? If you look in this region, this would be 8 right about here. Here's 6.5. And if we look, do you see we have these 2 groups of signals and they integrate to 5 hydrogens? That means that we have a phenyl ring with one substituent attached. Can you see that? And so just knowing that, we can look at an NMR spectrum, instantly tell that that's the case. And that's a huge part of that structure. A phenyl ring has 6 carbons and 5 hydrogens, and basically it leaves almost nothing left in that formula. So it's an example of that. Next, we have between 6 and 5, and these are hydrogens on alkenes. These are what we call vinylic hydrogens. Okay, and I said 6, it actually probably goes up higher than 6, but that's a general thing. And there would be other clues about this. For example, we could calculate unsaturations in our formula. We would probably see the alkene stretch in the IR. So again, there can be lots of evidence we can use to build up to the conclusion that we would have, for example, an alkene. The next region is really important. It's from 4.5 to 3.0. And these represent hydrogens on a carbon, and then the carbon is connected to a heteroatom like oxygen or chlorine or fluorine. You'll see that there's like 5 or 6 of these on the correlation table in this region. They all overlap. And so again, we have to take care, right, that we look and we say, oh, well, it's hydrogens on a carbon with a chlorine. No chlorine in the formula would mean, no, that's probably not right. But if you had an oxygen in the formula, oh, no, it's the oxygen instead. Do you see? The other issue with these is that they are additive. This is like an electron withdrawing effect. It's changing the electron density around the hydrogen. And so if you had, for example, 2 chlorines on the same carbon, those hydrogens would now not be between 4.0, 4.5 and 3.0. They would be higher. They would be up about 5.2. And 3 chlorines, actually, there's only one molecule that has that. It's called chloroform. And that's like 7.2, 7.3. I can't remember the exact number, but something like that. Okay. So it adds. So again, these are not fixed in stone. They're guidelines. The other thing about this is that when we have real organic molecules and we have a hydrogen attached to carbon, carbon has an oxygen, for example, well, that carbon can then have other carbons, or it could have hydrogens on it. And it turns out that the number of hydrogens changes the chemical shift. Basically, the fewer hydrogens you have, the higher the chemical shift number for the same type of group attached. So here's an example. If we have 1 hydrogen attached to a carbon, and that carbon has an oxygen and then 2 other carbons attached, so there's only 1 hydrogen total. We call that a methine group. And that's going to have a very high chemical shift, probably about 3.8. If instead we have two hydrogens attached to a carbon, the carbon has an oxygen, and then there's only one other carbon attached, we call that a methylene group. That's a really common term you probably ought to learn, CH2 methylene. That'll probably be around 3.5. If we have three hydrogens, well, then that's a methyl group. That means we have three hydrogens on a carbon, it's a methyl carbon, and then it has this oxygen attached. And that's going to come around 3.2. So you see the number of hydrogens causes it to change, but then we can flip that on its head. We saw that, for example, when we looked at our correlation table, we saw that alcohols generally come between 3.2 and 3.8. It's not perfect, but they generally come in that region. And so we know if we're at 3.2, it probably means there's a methyl alcohol, whereas if we're at 3.8, it probably means there's a methine, right? There's two other carbons attached, right? So it's a secondary alcohol, okay? All right. The next one I want to talk to you about is hydrogens on carbon attached to a phenyl ring, attached to a benzene ring. So it'd be something like this. Here's a CH2 attached to a benzene ring. These hydrogens would absorb. They would absorb between 2.2 and 2.8. Again, depending on how many there were, I probably have this number wrong, but 2.2 or 2.5, something like that, okay? We call these benzylic hydrogens. They are very common, okay? The next region is actually relevant to our example. Between 2.5 and 2.0, notice that they overlap. These can also be hydrogens on carbons attached to a C double bond O. So in other words, look here, here's a methyl group. It's attached directly to the C double bond O. Notice the double bond O, I'm sorry, the hydrogens are not on the carbon with this double bond O attached. They're on the carbon adjacent to it, okay? These hydrogens will then absorb in this region. The methyl one, for example, absorbing at the lower end at about 2.0. And if we had a methine, it'd be way up by 2.5. The last thing I want to show you is that alkane type carbons, alkane type hydrogens that are far away from functional groups or electronegative atoms, these generally absorb in the region 1.3 to 0.8. Okay, so using that information, let's go back. Let's look at our NMR spectrum here. So I'm going to look at two chemical shifts. I'm going to look at this one. If we look, arguably that's somewhere, it's almost 2.1. It's a methyl. So it probably represents a methyl attached to a C double bond O. Now notice also that there's zero neighbors, right? It's only one peak. These would have zero neighbors. They're like at the end of a cul-de-sac or something, right? So this, just the location of this peak plus the fact that it has zero neighbors, that's very, very strong evidence that we have this structure. In other words, if we go up here, it means that this methyl group, which was by itself, is attached to that C double bond O. Okay. The other chemical shift I want to look at is this one. Okay, so we know that this is a CH2, but coming up around 4, it means that the carbon of the CH2 is probably attached to an oxygen, right? Could be a fluorine, could be a chlorine, whatever, but we don't have fluorine and chlorine in our molecule. We do have oxygen, okay? And so Do you see the chemical shift location right there is indicative of the fact that we have this oxygen attached to that CH2. Now we know that that CH2 is also attached to a CH3, right? Because of the neighbors, because of the splitting. So that means this. See this CH2 is attached to that oxygen. Finally, then, do you see that we're only left with one more possible attachment, and that's attaching that oxygen on the other side to the C double bond O. Now, this looks a little weird, but we can rewrite this, right? We can start and say we have a CH3 attached to a C double bond O, attached to an oxygen, attached to a CH2, attached to a CH3. And this turns out to be the structure of our unknown molecule. So that's basically how we work the NMR. You don't have to do it perfectly in that order, but what you're trying to do is put together the clues and come up with your structures and show how they would all be connected together. All right, so that's basically all I have for you guys today. There is an assignment posted, so go ahead and start working on that. And next week we will we'll go through some questions. I'll give you some hints. I'll try to get you to kind of begin to put this together in your mind. And we may have one more of these. And that's basically almost the end of the semester there. So I'm going to go ahead and excuse you for the day. Let you start working on that. It's Friday, so have a great weekend. And I will see you guys next week. I will be in my office on Monday. Okay. And you guys take care. And I will see you soon. Yes, I will most definitely post the notes, the correlation table, the sample problems, everything. I just have to get to it. I'll get it on there, okay? All right, guys. I'll talk to you later. Bye-bye.